boiling water and raw chunks of iron were entirely sufficient to make multi-ton behemoths completely reshape the agricultural landscape. Deep inside a massive riveted cylinder, a roaring coal fire pushes hundreds of gallons of water far beyond its boiling point. The rapidly expanding vapor generates an immense internal pressure, transforming violent thermal chaos into a relentless mechanical drive. But a critical engineering paradox remained. How did pressurized steam transfer massive torque to the unpredictable ground without the guiding safety of conventional steel rails? The solution required abandoning finesse and embracing absolute physical excess. Engineers mounted these sprawling engines onto colossal iron wheels, utilizing an overwhelming structural weight to force the thick treads deep into the loose soil. These towering mechanical beasts conquered soft fields, muddy farm paths, and unpaved country roads, relying on nothing but extreme gravitational mass and superheated vapor. Inside their thick iron bellies, the heavy steel boilers simply roared. Containing this steam energy without rails demanded a massive foundation. The British from Lincoln needed 6 tons of steel and brass. It was pure Victorian elegance. Deep dark paint, delicate gold pinstripes, polished brass fittings caught the sunlight. Hundreds of exposed steel rivets bound the thick boiler plates. It looked exactly like a railway locomotive, only it roamed freely across open fields. But a harsh reality hid beneath those fine gold lines. The contrast was severe. Elegant Victorian finishes masked a filthy physical process. The hissing boiler demanded endless feeding, shoveling black coal, breathing thick smoke, sweating in scorching heat. The operator wrestled with heavy iron levers. He manually shifted simple, massive transmission gears. Raw metal grinding against metal, heavy iron clanking loudly. One missed gear meant lost momentum. This machine dwarfed ordinary agricultural equipment. A standard wooden horse cart weighed mere fractions of this beast. 6 tons of dead weight crushed the soft farm soil. The rigid iron frame absorbed every single bump. No shock absorbers, no pneumatic tires. Massive rear wheels transferred extreme vibration directly into the cabin. The internal physics worked tirelessly. High pressure built up inside the thick iron belly. Water boiled at extreme temperatures. The classic steam whistle screamed across the countryside. 2 parallel cylinders pumped thick iron pistons. Violent steam expansion converted into steady rotational force. Top speed reached barely 7 kilometers per hour. A slow, agonizing mechanical crawl. Fast walking pace, yet the continuous torque never dropped. Decades later, collectors still hunt these metal giants. Restored replicas occasionally shake the ground at historical parades. Enthusiasts polish the brass. They repaint the gold stripes. But the aesthetic appeal fades before the raw numbers. The true legacy lies in the sheer mechanical output. 16 steam-powered horsepower hauling fully loaded wooden wagons straight up a steep dirt hill. While 6-ton Clayton machines went for export, the appearance of 12-horsepower Lincolnshire tractors in local English fields caused sheer panic. During the late 19th century, agriculture still operated at the quiet, rhythmic pace of draft horses and oxen, until this heavy machinery altered the landscape forever. The Lincolnshire steam tractor introduced a 2-cylinder direct steam drive, paired with a horizontal boiler, delivering exactly 12 horsepower of continuous force. While that metric seems incredibly minor by modern standards, the steady steam release generated immense low-end torque, capable of dragging massive agricultural plows through dense, unyielding clay. Top speed hovered around 6 kilometers per hour, making the vehicle barely faster than a walking man, because raw, unstoppable pulling force dictated the entire engineering philosophy. Operating this early agricultural pioneer demanded immense physical endurance and absolute concentration from the driver. The machine completely lacked any form of suspension system to absorb the brutal impact of the terrain. A heavy, rigid frame built from forged steel rested directly on massive iron wheels. Every hidden rock, deep rut, and frozen clump of earth transferred harsh kinetic energy straight through the solid metal chassis directly into the operator's bones. The ride was violently punishing. Navigating the uneven fields required wrestling a heavy single-speed manual transmission while simultaneously managing a highly volatile and dangerous power source. The driver had to constantly monitor and maintain optimal boiler pressure under a heavy load, knowing a sudden pressure drop meant stalling in deep, wet mud. An acrid, suffocating cloud of thick coal smoke and burning lubricating oil continuously washed over the open platform, stinging the eyes and filling the lungs. This drastic transition from organic animal muscle to heavy industrial mechanization completely shocked the unprepared rural population. The sheer visual weight of exposed steel rivets, constantly turning massive metal wheels, and a towering smokestack created an overwhelming physical presence in the previously quiet countryside. When local farm laborers first encountered this hissing, smoke-belching metal machine grinding heavily along a provincial dirt path, they genuinely believed they were witnessing a derailed railway locomotive tearing violently through their agricultural lands. English 12 horsepower faded against the American Midwest, where the IHC Mogul tractor required 30 horsepower just for its own movement. The scale of farming shifted completely. The Great Plains span over 1 million square kilometers of vast, unforgiving territory. To conquer this immense physical expanse, International Harvester built a mobile power plant on wheels. The engineering numbers define the sheer brutality of the machine. 30 horsepower drives the traction unit forward. 60 horsepower powers stationary operations, running massive threshers and sawmills. A colossal steel radiator dominates the entire front profile. Heavy iron wheels, standing almost 2 meters tall, carry the rear structure. Massive metal lugs bite deep into the dry prairie soil with every slow rotation. The rigid frame takes every violent impact from the uneven ground. There is no suspension, just raw, unrelenting weight crushing the earth. A low, rhythmic rumble of twin horizontal cylinders echoes across the open fields. The sharp, acrid smell of burnt kerosene fills the surrounding air. A primitive but reliable hot tube ignition system forces explosive torque through a single direct drive gear. Top speed barely touches 5 kilometers per hour. Speed means absolutely nothing here. The sole objective is pure, uninterrupted pulling force. The Mogul easily drags a massive 12-blade plow through the tough Midwestern dirt, tearing up deep terrain that quickly broke lighter machines. It pulls tens of tons of heavy cargo from sunrise to sunset without ever stopping. But this sheer mechanical force soon reached an excessive limit for basic agriculture. Realizing that the raw power of the IHC Mogul overmatched simple field work, engineers found a new physical target. They redirected this massive iron beast to transform the landscape itself. The machine began compacting heavy earth and carving out entirely new roads. A heavy metallic thrum shakes the ground at a Minnesota festival, accompanied by the continuous deafening blast of high-pressure steam. An original, fully operational agricultural machine from 1906 completes a 3-kilometer loop, crushing the dirt beneath its steel treads. This is the Advanced Thresher steam engine. By 1906, the United States railway network had rapidly expanded beyond 340,000 kilometers of track. The engineers at the Advanced Thresher Company absorbed that vast industrial momentum, intentionally erasing the boundary between a freight locomotive and a field tractor. Why does an agricultural machine require the exact aesthetic and structural design of a locomotive? To dominate local county fairs and demonstrate absolute mechanical supremacy in heavy load-pulling competitions. Visually, the machine creates a striking contrast between the demands of dirty farm work and the imposing presence of a train. A towering front smokestack, massive side water tanks, dark industrial paint, and ornate gold accents make it look like a rural shunting locomotive rolling straight through a wheat field. Starting the boiler demands intense physical labor and precise thermal management. The operator shovels coal directly into the firebox, gradually bringing hundreds of gallons of water to a boil until the internal boiler pressure reaches a critical working threshold. Thick iron valves open manually, forcing superheated steam into a massive vertical twin-cylinder engine. The system generates 30 horsepower. It transfers that raw, expanding thermal energy straight into massive iron rear wheels. Heavy steel cleats bite deep into the loose topsoil, ensuring maximum mechanical grip. The machine features absolutely no suspension system. Instead, it relies entirely on its sheer physical mass for stability across uneven terrain. Weighing in at 9 tons, the Advance matches the structural weight of a standard early 20th century wooden railway boxcar. This immense downward pressure allows the tractor to scale steep, muddy inclines and steadily haul loads exceeding 13.6 tons at speeds up to 7 kilometers per hour. Every single mechanical action depends on brute force, balanced by the operator's careful control of internal pressure. Today, this exact American engineering philosophy survives in motion. Every year, a surviving original 1906 Advance machine fires its boiler to run that vintage machinery festival route, converting raw steam into kinetic power exactly as it did over a century ago. 9 tons of American exhibition steel surrendered. 10 tons of British cast iron claimed Buckingham Palace. American machines pulled festival weights. British machines built actual empire foundations. Aveling and Porter engineered pure pragmatism. Workers renewed the facade in 1913. This roller prepared the surrounding avenues. 20 horsepower, 10 solid tons. A coal-fired boiler fed the steam engine. The iron belly boiled water. Steam built up inside. Pressure reached critical levels. Twin cylinders trapped the energy. Engine specs mattered less than gravity. The design focused on downward force. There was no suspension system. Zero shock absorption. A completely rigid frame. It directed mass straight down. Maximum pressure hit the terrain. The front roller spanned 1 meter. It equaled the width of a bank vault door. It struck like a massive mobile anvil. Rear wheels followed the exact path. They crushed loose soil. They pulverized gravel. Weight forced the stones to interlock. Air pockets collapsed under vertical load. Earth compressed into dense pavement. The machine obliterated the natural unevenness. Muddy trails turned into transit arteries. It compacted the empire. Streets became flat surfaces. Operating speeds stayed between 3 and 6 kilometers per hour. A steady, crushing crawl. No fast gears, no quick turns, just constant downward compression. Heavy metal reshaped the English landscape. Direct mechanical action ruled the process. The operator commanded forward motion and ground compression entirely through manual boiler pressure management at the central valve. The experience of compacting London asphalt allowed British engineers to build a machine for a vastly different mission. John Fowler and Company designed an industrial heavyweight specifically to rescue trains in the unforgiving extremes of India. Colonial expansion required immense mechanical force to conquer vast unpaved landscapes. The Indian railway system operates on a broad track gauge measuring exactly 1,676 millimeters. This exceptional width makes local locomotives and cargo wagons massively heavier than standard European rolling stock. Moving these colossal weights through rural territories demanded an unprecedented level of mechanical power. When a massive train derailed in a remote province, standard recovery methods simply failed. The Fowler steam tractor arrived to dominate the recovery zone. It weighed over 7.7 tons of pure exposed metal. Engineers installed zero suspension. Raw gravitational mass pressed the wide steel wheels deep into the loose soil, ensuring a permanent mechanical grip. The inline twin compound engine produced a relentless 25 horsepower. It delivered constant torque directly to the heavy rear drive axle. A crippled locomotive lies buried in the dense dirt. The Fowler tractor rolls heavily toward the crash site. Thick iron drive rods clank sharply with every slow wheel revolution. High-pressure valves release deafening bursts of boiling steam into the humid air. Workers drag heavy chains through the mud and hook thick steel towing cables onto the cast iron frame of the fallen train. This wheeled beast completely replaces a traditional railway rescue crane. The operator fully opens the primary steam throttle. Boiler pressure converts directly into brute pulling force. The thick cables snap tight. The tractor drags the derailed mechanical giant across the rugged ground, forcing the heavy iron wheels back onto the steel rails. 8 kilometers per hour while towing a dead locomotive. Absolute traction overrides the unstable terrain. The wide steel wheels refuse to slip. Massive towing capacity transformed impossible recovery missions into standard daily operations. The driver controlled this overwhelming physical power using a heavy-duty manual gearbox featuring exactly 2 primary gears. 25 horsepower failed the Australian wastelands. The 14-ton BB1 model headed there. The required traction was enormous. The tractors left rural England behind. A brutal new continent awaited. John Fowler and Company built a monster. Twin compound cylinders generated 50 horsepower. Torque snapped massive iron chains. Maximum speed hit 6.4 kilometers per hour. Speed meant nothing. Brute force dictated every movement. The tractor dragged 27.2 tons. The chassis design ignored conventional rules. Suspension systems did not exist here. 14 tons of steel needed no springs. Gravity ruled. Dead weight pushed iron into dirt. Wide-flanged wheels crushed unstable soil. Grip remained constant. Traction never broke. The massive machine crawled forward. Dual water tanks flanked the heavy boiler. High-pressure steam filled the metal pipes. Boilers screamed under the intense heat. Thick smoke blackened the clear sky. Heavy vibration shattered the dry air. The mechanical roar echoed for miles. Ground shook under the heavy iron treads. The Outback surrendered. British loggers tested these machines first. Australian rail engineers took over later. Infrastructure projects required raw mechanical power. Steam tractors hit their engineering peak. The physical limits became very clear. The era peaked. These steel beasts abandoned the gentle 3-kilometer museum loops to tear through the desert and forge the grueling 2,900 kilometers of the Trans-Australian Main Line from Adelaide to Darwin. 60 horsepower pulling 45 tons of steel without a single spring. This is the Fowler B6 Superlion in motion. Pure mechanical violence locked inside a massive red and gold chassis. Inside the iron belly of the boiler, pressurized steam forces its way into twin compound cylinders. The resulting energy bypasses any flexible components. There are no shock absorbers. There are no rubber tires. Instead, immense torque travels through a heavy-duty multi-gear manual transmission directly to a rigid rear axle. The power meets the earth through colossal iron drums. Deep metal flanges cast into the wheels bite aggressively into the unstable soil. Iron crushes stone. The massive rear wheels rotate in a relentless cycle, carving deep trenches into the uneven terrain while towing a payload equivalent to the weight of a modern commercial airliner. 45 metric tons drag behind the tractor. Despite the overwhelming mass, the machine maintains a steady pace of 9 kilometers per hour. A distinctive, dry, roaring exhaust note blasts from the chimney, vibrating against the surrounding landscape. The sharp smell of burning coal and hot machine oil fills the air. Without a suspension system, extreme loads on rough roads should theoretically shatter the chassis. The Fowler engineers solved this problem through pure material scale. The extreme mass of the vehicle itself becomes the dampener. The heavy iron frame and the water-filled boiler absorb all kinetic impacts from the terrain. This immense weight forces the iron wheels downward, maintaining absolute traction where lighter vehicles would bounce and lose grip. Solid mass defeats the broken ground. Operating from an enclosed cab, a rare structural feature for steam traction, crews commanded these machines to drag steel bridge girders, mammoth stone blocks, and complete telegraph tower sections across barren landscapes. The heavy engineering of the Fowler B6 proved so indestructible that these iron beasts remained in active commercial service, hauling extreme loads through remote industrial zones well into the late 1940s. While Fowler traction engines dragged heavy steel bridge girders across barren landscapes, the Burrell Special Scenic models hauled electricity directly into British towns. Built by Charles Burrell & Sons, these machines were not just heavy transportation vehicles, they were autonomous power plants. In the early 20th century, rural Britain still lived in darkness after sunset. Traveling funfairs required massive amounts of energy to illuminate their complex mechanical attractions, and local electrical grids simply did not exist. Burrell engineers solved this structural deficit. Underneath the bright paint and polished brass trim sat a highly efficient compound twin-cylinder engine paired with a high-pressure boiler. The steam system generated exactly 25 horsepower. During transit, this mechanical output moved heavy carnival rides and equipment trailers from settlement to settlement. The manual gearbox allowed the rigid iron frame to negotiate steep slopes and rough urban terrain at speeds reaching 10 kilometers per hour. That pace defied expectations. A heavy metallic structure pulling dense cargo rarely moved so fast. But the true mechanical breakthrough happened the exact moment the iron wheels stopped rolling. The traction engine immediately transitioned from a towing vehicle into a stationary energy distribution hub. Long leather belts connected the spinning heavy flywheel to front-mounted dynamos. High steam pressure converted directly into raw electrical current, a mobile power station. Operating steadily from 1905 until 1930, these engineering marvels physically electrified the British countryside long before national power grids reached those isolated regions. Coal burned intensely in the firebox. The heavy iron flywheel continuously drove the mounted dynamos, and this mechanical rotation sustained the steady glow of hundreds of incandescent lamps across the dark fairground. From lighting British fairgrounds, heavy engineering shifted focus to terraforming the vast American continent. Here stands the JIK steam tractor. Maximum scale. Physical limits pushed to the absolute extreme. A massive two-cylinder steam engine drives this colossal mechanical beast, generating an unprecedented output of 110 horsepower. The sheer mass hits 18 tons, matching the weight of 3 adult African elephants. Steel meets earth. Tremendous weight drives the traction. Solid metal wheels measuring 2.1 meters in diameter bite deep into the tough prairie soil with heavy steel spikes. Intense vibration rolls through the ground. Deep ruts form instantly. The sheer weight of the 23-foot-long steel frame keeps the entire structure grounded without any suspension system. Every shock transfers directly into the heavy chassis. Massive torque rips the dirt apart. 30 heavy plows drag behind the massive rear axle simultaneously. Flat Dakota plains break open under the tremendous pulling force. Operating steadily at 4 miles per hour, this moving powerhouse systematically tears up the thick Midwestern territory acre by acre. The visual scale completely defies standard logic. The main boiler easily dwarfs a grown man standing right next to the firebox. Intense heat radiates. Thick smoke billows. The operator sits high above the ground, steering this mechanical giant like a captain commanding a slow iron ship. High-pressure steam blasts continuously from the tall chimney. Short gear ratios grind under extreme tension. This massive torque output allowed a very small crew to prepare thousands of acres of agricultural land in just a single day. It transformed wild landscapes into commercial farms. Today, only one fully original unit survives in working condition. Historical foundations maintain this last surviving machine. It physically demonstrates the raw mechanical power of the early 20th century Industrial Revolution. In 1988, this 18-ton agricultural monster successfully towed a full-size railway locomotive across a solid demonstration field. A locomotive in tow behind a tractor is the final point of an entire technological era. For decades, these mechanical titans formed the physical backbone of global infrastructure. They plowed thousands of acres of agricultural fields. They crushed stone to lay early road construction networks. They hauled raw timber and heavy steel across vast industrial yards. Then the 1920s brought an irreversible shift. Lighter internal combustion engines rolled off assembly lines. Liquid diesel replaced raw coal. Compact cylinder blocks, weighing just a fraction of the iron giants, pushed out massive pressurized boilers. The transition was absolute, yet their engineering DNA remains completely intact. Extreme torque distribution and rigid chassis designs built the exact mechanical foundation for all modern heavy construction equipment. The fires finally went out. The frozen steel frames of these steam giants stand silent, surviving today only in heritage museums and at rare historical demonstrations.